Good evening, one and all present here. We are here for week 4 live session of the NPTEL course Urban Utilities Planning, Water Supply, Sanitation and Drainage. I am Monica S. I am a PMRF candidate and research scholar at the Department of Architecture and Regional Planning, IIT Kharagpur. The course is handled by Dr. Devapratim Pandit, who is also an associate professor at the same department. So, running through the template of the course, as usual, we have an interaction or a problem solving session every Monday, 7 p.m. to 8 p.m. for the next few weeks. After every question, we can have after a prompt, you can raise your hand, unmute, and bring up your query. And questions can also be posted in the chat box, which will be taken up hopefully within the session, during the session or towards the end of this session. Then we also have a discussion forum for the course where any questions related to the live sessions, also the regular sessions can be raised. Where questions will either be addressed in the forum itself or in the next week's live session. So, a short recap of what was taught in week 4, pumping and storage. So, lecture 16, we looked at pumping stations, different types and types of pumps. In lecture 17, how they work, the mechanisms. Lecture 18 looked at the sizing of pumps, and 19 and 20 looked at service reservoirs, which are essentially water storage or reservoirs which are part of water supply distribution networks. So, I think 7-5, so we'll get into the lecture. So today we'll just be looking at a few assignment questions from the previous round of the course. So first question, dash is used when there is suspended matter, acid or alkali, which may damage the pump. A, displacement pump, B, airlift pump, C, impulse pump, and D, centrifugal pump. Does anybody know the answer? You can post in the chat box.
Centrifugal pumps.
Okay. We've got one answer. Anybody else? Any other answers? Okay, so the answer can be seen in this particular slide of the lectures that were posted for week 4. So the answer is actually airlift pump. So the thing is, when you have some kind of suspended matter or acid or alkali, and you have a pump that is dealing with the water that has all of this, what happens is these components can damage the parts of the pump. So whenever there is a moving part or a metal based part, the suspended matter can go get deposited, or in some form or the other, this moving part actually gets damaged heavily. However, in an airlift pump, if you remember, it's mostly through the introduction of compressed air that we end up. So if you look at, let me take, sorry. If you look at this mechanism, so compressed air is thrown in at a great pressure through this pipe. What happens is this airlift pump is immersed in water, and through this educator pipe, which is all placed within this casing or air pipe, what happens is this flow of air sort of gets mixed with the water, and both of them, a mixture of air and water, starts flowing out. So that's the mechanism. In this, it wouldn't matter so much if there is suspended matter, or if the water is acidic or alkaline uh, in this setup. So that's the advantage of the setup. So our answer is airlift pump. In fact, in a centrifugal pump, suspended matter of like bigger sizes are problematic. However, if you notice, there was this one lecture on sewage distribution and the pumps involved. Centrifugal pumps there do handle suspended matter, but even then, uh, the better option to go for is actually airlift pump. So sewage, the issue with sewage is the density of sewage is going to be so high that airlift is probably not going to be the best option. However, without giving specifications on the kind of density that we are dealing with, assuming that we are looking at only water supply, then airlift pump is the standard way to go. So I hope that clears the next question. From a clear water reservoir, 8-meter deep and maximum water level at 50 meters, water is to be pumped to an elevated reservoir at 100 meters at a constant rate of 5 lakh liters per hour. Distance is 1000 meters. Calculate the brake horsepower of the pump. Assume economic diameter of racing wheel and F is equal to 0.01 and efficiency is equal to 90%. So, what we are looking at here is, let me, we have a clear water reservoir from where we are going to take water. So this is going to be our input, right? So, and the depth of this reservoir is 8 meters, right? This reservoir, the maximum water level is at 50 meters, which means relative to a ground level, this is at 50 meters high, right? And we are going to pump this water to an elevated reservoir at 100 meters high. So we are going to pump it to a point that is 100 meters high, right? So you have a reservoir here. We are going to take it from here and make sure we are pumping it. So we're taking it from here and pumping it to, right? Pardon the bad drawing. I'm using a mouse. So at a constant rate of 5 lakh liters per hour. So the thing is, these two are not actually located close by. These two are located at a distance of 1000 meters, that is 1 kilometer. What we need to do is calculate the brake force power of the pump. So all of this, shifting this whole water from here to there, will basically be done using a pump, right? So we need to be calculating the brake horsepower of this pump. They've asked us to assume economic diameter of rising main F is equal to 0.01 and efficiency of the pump to be 90%. So if you remember the lectures, we saw that water horsepower of a pump is basically the discharge in kilogram per second into total head divided by 75. So what is this discharge in kilogram per second? We need to basically take water discharge from the input, whatever is being discharged by the pump in meter cube per second, and we should also be taking into consideration water density. So for getting this kilogram per second, we'll be using kilogram per meter cube into meter cube per second. So we'll be multiplying W and Q as well as the total head. So if you remember, the total head is calculated by adding three components. One is suction lift, one is discharge lift, and one is head loss. So in our particular case, in this case, the pump can actually be located anywhere, right? Like we can locate the pump immediately at whatever level we want to. Right? But immaterial of that, we will need to calculate these three. So head loss will be basically because of friction losses when you carry water through any channel or any pipe, any distribution. What happens is we will end up, because of the friction that you undergo, or say it enters a particular equipment or it exits a particular equipment. In all of these movement of water, what happens is we will end up facing a bit of friction, due to which we will lose pressure. So head loss is essentially, say when you're looking at this setup, let me change the color. So this is one reservoir and we are taking it to this reservoir, right? The thing is, in the conveyance of this, say we calculate the head to be just the total amount of height that we need to take it for, we will end up losing out. The pump might not actually be able to deliver the water because a lot of pressure is being lost in the conveyance of water in the means of friction. So that is the third component. And given in the question is assume economic diameter of racing line. So when we are using a pump, so this is the pump, and we are using water mains, the diameter of this pipeline, they've asked us to assume it to be the economic diameter. So what is the formula for economic diameter? Do you remember? Use Leah's formula. Leah's formula is, we take it to be 0.97 to 1.22 of the square root of Q. Q will be discharge in meter cube per second, right? So that will be, so discharge into total head will give you the water horsepower. However, water horsepower is the work actually done by the pump, right? But when you convert any form of energy from form A to form B, in this case, what we are doing is we have a pump where it's either going to be run by fuel or it's going to be run by electricity, right? So we are converting, say it is an electric, like electric motor. So we are going to convert electrical energy into mechanical energy, which is going to manually push the water from the lower reservoir to the upper reservoir. So in this conversion, the thing is, not all machines will be able to convert this amount of the transition from electricity to mechanical energy completely. So there will be an upper there will be an efficiency that is marked with the pump. So currently we are assuming an efficiency of 90%, which is also accounted for here. So we, after we calculate the water horsepower, what we do is we also calculate the brake horsepower by dividing the water horsepower by efficiency. Let's just work out the problem. You will be able to see what is it. So these are the given details. Discharge is given to us in as 500 liters per hour. Mind you, the unit we require is meter cube per second, but it is given in liters per hour. The depth of the input reservoir, that is the lower reservoir, is 8 meters. The altitude of this input reservoir is 50 meters from, say, some reference point. It could be mean sea level or any other reference point that you're fixing. And the elevated reservoir altitude is 100 meters. So, and these two reservoirs are located at a distance of 1000 meters. Uh, we have been asked to assume an F value of 0.01 and an efficiency of 90%. Yes. What we'll be finding out will be the brake horsepower of the pump, and we'll be using this formula for calculation. So firstly, let's take the discharge value. We need to convert it from liters per hour to meter cube per second. So, one second. Sorry about that. So firstly, we're going to convert it from liters per hour to meter cube per second, for which we divide by 1000 because liters to meter cube, and divide by 3600 to make it per second, right? So then we get the value 0.139 meter cube per second. So that is our Q value. Then we calculate the economic diameter of the rising main, essentially the diameter of the pipe that we are going to use to convey the water. So currently we have a range, right? Like, sorry, this. Currently we have a range which is 0.97 to 1.22 root of q. So we substitute the calculated value of q here to get the range of diameter. So the diameter range is going to be 0.36 to 0.45 meters. That will be our unit. Then we calculate the total head. So total head will be suction lift plus this discharge lift plus head loss. So the component of suction lift per discharge plus discharge lift, we essentially have to just look at how much the depth of the input reservoir is, which is 8 meters. So we're just going to take the depth and the difference between the heights, the altitudes of the two reservoirs. So this will be 50 meters and 100 meters. So 100 minus 50. So no matter where we locate the pump, the sum of suction and discharge lift will be the same. I hope I'm being clear here. So if we look at the diagram that I drew here, no matter where we locate the pump, so say we locate the pump here, somewhere here, right? Then this will be the suction lift and this will be the discharge lift, right? So alternatively, say we so this is location 1, or say I put the pump here, this will be the suction lift will be here and the discharge lift will be here. So you see this entire suction lift plus discharge lift will be the same no matter at which altitude I am placing the pump in. So it doesn't matter to us where exactly we're placing the pump. So here the suction lift plus discharge lift will be 58 meters because the difference in altitude is 50 meters plus the depth of the input reservoir. So we are carrying all of the water from one reservoir to another. Then for the third component, we should be calculating the head loss due to friction, for which we use the Darcy-Weisbach formula. I hope you remember the formula. So currently we have this Fanning's friction factor. So Fanning's friction factor will be multiplied by 4 to get the Darcy's friction factor. And Darcy's friction factor is what we use in the formula. This is the formula. Why are we not using this? So how are we coming from this formula to this formula? So we have this Q is equal to VA. If you remember the basics of flow, uh, this will be the, this is where, because we are substituting this formula here, we'll be using this equation. So the head loss in pipe will be F dash into L into Q square divided by 2G into pi by 4 the whole square into d power 5, essentially, right? So now from the previous calculations we have two values of d. It can either be 0.36 or 0.45. So let's do the calculation for both. So when we take the diameter of the rising main to be 0.45 meters, then so f dash is 4 times f. So this is 4. This is the value of f into L. L is the distance, so length. and Q is 0.139 as we had calculated in meter cube per second, the whole Q square divided by 2 into G is 9.81, the gravitational constant, and then pi by 4 the whole square into, here we are taking D to be 0.45, right, and the value comes down to be 3.46 meters. If we take D to be 0.36 meters, the second value that we got, then substituting all the same values except D will be 0.36 here, right? This value alone will change. So we get 10.56 meters. So we get two different values for head loss. So now we calculate total head. So we had already calculated the suction lift plus discharge lift to be 58. Plus now we are getting a head loss of either 3.46 meters or 10.56 meters, depending on the size of the diameter that diameter of the pipe that we are using. So we get two values again. So this is from this value, and this is from this value, right? So we are getting two different values of total head. It is either 61.46 to 68.57 meters. So now we have um, the total head value as well as discharge value. So we have one component of discharge in fact. So we need to calculate it. So right now we have discharge in meter cube per second, right? So for obtaining it into kg per meter cube will be the density of water. So the actual density of water is 997. We are going to round it off to 1000, right? So this is the density of water into 0.139. That will be the discharge of water in meter cube per second. So this total thing will be discharge kg per second, and the total head. So we take one of the values 61.46 divided by 75 into efficiency, because for calculating the brake power we need to divide it by efficiency, and it's a 90% efficiency count. The other value that we'll have is, so this value, this is the other head loss value that we got from the Darcy-Weisbach calculation using two different racing bend diameters. So then we calculate both, we get this answer, 126.56 HP to 141.18 HP. So that will be the answer for this numerical. Any doubts? It's just a matter of remembering which equation has to be used where, and what is the sequence of equations. Are there any doubts in this numerical, or do you want me to repeat any of the steps again? I hope I was clear. Right, so basically we first calculate the discharge in meter cube per second. Then we find out the economic diameter of the rising main, which will give us a range of values, right? Then we calculate uh, head loss in the pipe due to friction. Then we calculate the total head using suction lift, discharge lift, and head loss. And then we calculate the range of brake horsepower, right? Okay, moving on to the next question. The service reservoir design depends on A. Reservoir capacity, B. Topography of the site, C, cost of materials, that is concrete, reinforcement, and formwork, or D, all of these. Any answers? Okay, you've got one person saying D.
Topo- Topography of the site.
Ma'am, the actual answer is D. Ashwin is right. Uh, the answer is all of these. So if you notice this slide, the answer is actually lifted right out of this. So the service reservoir design will depend on reservoir capacity as to how much capacity do you actually need. How much does the area require or the city require. The topography of the site, the thing is, if the service reservoir needs to be located at a higher altitude or the lower altitude. So higher altitude is where we would expect service reservoir to be located, because from there gravity flow can take the water to the distribution network and then give it additional head. So the topography of the site becomes very important. Subsoil type, because the capacity of the soil to actually be able to hold that much water, or the structure or weight of the structure would also matter. Beyond a point, it becomes too costly to have a service reservoir in certain areas, and the cost of material. So we will want to optimize the amount of material going in. So all of these will dictate service reservoir design, right? So the answer is all of these. The next question. Total storage capacity of a storage reservoir is the sum of A, balancing storage plus breakdown storage, B, balancing storage plus fire storage, C, breakdown storage plus fire storage, D, balancing storage plus breakdown storage plus fire storage. Any answers? Yes, Ashwin, you are right. The answer is balancing storage plus breakdown storage plus fire storage. So, my slight recall, fire storage is the amount of water that you require for firefighting. Since the reservoir is already there and it's going to carry water anyway, we'll be using that water for firefighting. Breakdown storage is just in case there is an issue in the distribution network, or uh, before the service reservoir, or there is an issue in the water treatment plant, or any such issue where the supply of water is going to break down for some time. Excuse me. So the balancing storage is basically, so if you remember from the lectures, throughout the day we have differential requirements for water coming from different households, different uses, different land uses. So what happens is, when you cannot just keep modifying the amount of water that you're taking out of a reservoir and treating and then giving it to these distribution network. You can't keep changing it, because the demand is going to be dynamic. We don't know when the demand is going to increase, decrease. Even if you know approximately, we can't expect the water to exactly be the amount that is being supplied, which is why we basically have a storage reservoir where we ensure that there is enough water stored in order to cater to this variation in demand. So that is the balancing storage component. So the answer is D, balancing storage plus breakdown storage plus fire storage. Right. So any questions till now? Any issues in the explanation? Anything?
Please repeat balancing storage.
Okay. Actually, there is one problem where we will be working out the balancing storage. I think when you get to that, you'll understand the balancing storage part. Is that all right?
Okay, no problem.
Yeah, yeah. So, okay. So the next question. Um, one sec. So question 14. So pump sizes are determined based on annual average daily consumption, annual maximum daily consumption, peak hour consumption on annual maximum day, or B, annual average daily consumption and annual maximum daily consumption. C, discharge head and flow needed at the point of connection, or D, basically all of the above. Annual average daily consumption, annual maximum daily consumption, peak hour consumption on annual maximum day, discharge head and flow needed at the point of connection. So, any answers?
A.
Okay. Anybody else? So, ma'am, you're actually right in the sense that these are the three things that are actually given in the slide, right? So, annual average daily consumption, annual maximum daily consumption, and peak hour consumption and annual maximum day. However, if you look at the explanation that is given above, so pump sizes are determined as per the discharge head and flow needed at the point of connection. So, these are also important components in the determination of pump sizes. So I know it's a little confusing, because it's given here in highlights and this explanation is given here. Essentially, using all of this, we are determining the flow needed at the point of connection, right? But the answer, since the option also covers this, that will be your answer, D. So make sure you, I know it is a repeat of what is already being addressed, but that is, this part is, the first three options are essentially used to calculate this part. But yes, the answer ultimately is D. Uh, all of the above, essentially, right? So make sure you take this also into consideration. I know the text should have probably been clearer. Yeah. Okay. So this is where we'll understand balancing here. Balancing storage in this numerical. So, calculate the storage required to supply the demand shown in the following table. If the inflow of water to the reservoir is maintained at a uniform rate throughout 24 hours using the following data. So, in the lecture that was given, we were introduced the mass curve method, right? And Sir had used uh, a problem. He had worked out a problem where a population was given, the LPCD is given, right? And we calculate the hourly supply and the hourly demand is given in terms of percentage, right? So this is what is explained in the class. However, the data that we have right now is slightly different. Here we have demand in million liters, it's not actually a percentage, so be mindful of this. They've given us the demand, so they have not given us values on what the population is, or what is going to be the hourly supply, hourly demand, nothing. So they've just given directly, this is going to be the hourly demand in this city for 24 hours, right? So when we are about to, how do we figure out? So there are two components to solving the mass curve. If you remember, we have the supply line and the demand line, right? So here also this is the demand line and this is the supply line. Here this is the supply line and this curve is the demand line. So how do we figure out what the, we have demand here? How do you figure out what the supply is? So the basic assumption that we are going to go with is that we are going to equate demand and supply, right? We're going to take, okay, the amount of water being demanded is the amount of water that we're going to supply. However, this supply, the assumption that we are given is at a uniform rate throughout 24 hours, right? So it's going to be a 24-hour supply. If you remember again in class, yes, Rahul, total demand is equal to total supply, absolutely. So this is going to be a 24-hour case. Again, in the class, we were explained two cases. One was a 12-hour supply and one was a 24-hour supply. Currently, in our problem, we are going to use 24 hours supply. right? So let us first figure out how much the total demand is. So this is essentially what is given in the problem. So these are the time periods 0 to 1, 1 to 2. So 0 to 1 is like 12 a.m. to 1 a.m., 1 a.m. to 2 a.m. till midnight, 23 hours, 11 o'clock to midnight, right? So this is our hourly demand. And mind you, again, it's not a percentage, they've given us the value, right? So how do we figure out the cumulative value for this? It will be zero point 0.1, the first value. Second value will be a sum of these two, right? Third value will be a sum of these three, right? Zero point 0.1 plus zero point 0.1 plus 0.15 will be 0.35. Or alternatively, you can keep adding these two values, the previous cumulative value plus the current cumulative value. So let's work it out on Excel. So excuse me. So this is the uh, value that we've been given, right? So first value will be the same. Second, we add this plus this, right? Third, we add 0.15 plus how much ever the cumulative value is till now, and we continue to do this for all the. So if you see here, this is zero point 0.1 plus whatever the previous cumulative value is, and we ended it ends up being 5.95. So that will be the total demand of the particular city for 24 hours, right? So I figure out that the total demand is 5.95 and it's a 24-hour supply. So firstly, as Rahul had also pointed out, we equate total demand and total supply to be 5.95 million liters. But we will be supplying water for 24 hours. So the hourly supply will essentially be 5.95 divided by 24 hours, like 24, right? The number of hours. So we get approximately 6 million liters. So instead of going to the nitty gritties and taking tiny, minute values, let us go ahead and take it as 6 million liters. It's not going to make much of a difference for us in terms of storage. So what we do is we take it as 6 million liters, right? Divided by 24. Sorry, it's this one is not completed here. So what we do is we take 5.95 divided by 24 will give you 0.25 hourly uh, hourly supply. 0.25 million liters will be our hourly supply. So we continuously in the city we give an hourly supply of 0.25. So all of these values will be 0.25, right? We are essentially rounding it off, correct? So when we do that, then we figure out the cumulative hourly supply. So in the first hour we would have supplied 0.25. In the second hour it will be 0.25 plus how much ever has been supplied, so 0.5. In the third hour it will be 0.25 plus, so 0.75. This much water would have been supplied till 3 o'clock. So if you notice, it comes out to be 6 million liters, right? So hourly supply is 0.25. Pardon the. We have an hourly supply of 0.25 million liters. So then what we do is we figure out the difference between the supply and the demand, right? So we find out cumulative supply minus cumulative demand, right? So we calculate this number for all of them. So for example, here for 8 to 9 p.m. we takes cumulative hourly supply and then subtract cumulative hourly demand from this, right? So we get the values of the difference, which is also given here. So if you notice, we'll have to be figuring out the maximum positive value and the maximum negative value in this difference. So it's highlighted here. So what does the maximum positive value depict? It basically represents the maximum excessive supply that is happening. So the demand till 5 a.m. in the morning is just zero point 0.7 million liters, right? However, we will be supplying 1.25 because we are going to constantly supply water, right? So we'll be supplying 1.25. What happens here is, because this water is being supplied, we can't just let it go waste, right? Because if you notice from these negative values, there is going to be a period of deficit. Okay, let's take 12 o'clock to 1 o'clock. By then the city would have required 3.4 million liters of water, but how much we would have supplied is 3.25 only. We will require more water. So what happens is, there are time periods in the day where the city requires more water than has been supplied, and there is a time period where the city supplies more water, or rather the city's water distribution network supplies more water than has been asked for. So this excess positive value, highest positive value, depicts the maximum excess supply that is coming in the network, right? The other value is maximum excess demand. So there'll be one point where zero point 0.7 million liters of water is required more than what is being supplied, right? So if you notice this 4.75 and 5.45. Sorry. This 4.75 and 5.45, what happens is the city actually requires zero point 0.7 million liters more water. So in order to figure out how much should our reservoir be, our reservoir should have the capacity to address these two maximum ordinates. We call it ordinate. So the total storage required is calculated by adding these two values. So adding 0.55 and minus zero point 0.7. So that will be our total storage required. So to answer your question, ma'am, this will be your balancing storage, right? So this will be the difference between how much is being supplied. So whenever you are supplying into a reservoir, say constantly there is water coming in and constantly there is water going out also, right? However, we should be adding this value. This will be the balancing storage. So this will balance this difference in supply and demand that is happening in the city. That is why it's called balancing storage. I hope the that answered your question also, right? So that will be our answer for this. So in this case we are not taking into account the fire demand and the breakdown demand. So if you calculate that as well, then the value will be slightly higher. So breakdown demand is usually 25% of what is required per day, or 1 to 2 hours of uninterrupted supply, if I'm not wrong. And fire storage will be 5 liters per capita. So any queries in this? I hope the explanation was clear. Okay. Any queries, anything? Yes, Mr. Rahul, we might have such numericals in the examination as well. It's, if you look at it, it's quite simple actually. If you're not going wrong arithmetically anywhere, which was the biggest issue for us during masters. Any other queries? Any other issues? Any other feedback regarding the live sessions? If you would prefer anything else being discussed as well. Use of online calculators during exams. I am actually not familiar with the examination guidelines, so to say, but I will get this cleared. I will either post on the discussion forum or I'll let people know here. I'm sorry, I'm not sure about it. So the thing is, in case you're expected to calculate things manually, then the numbers will be quite simple. Just don't make arithmetic mistakes though. And again, if I'm not wrong, I don't think you'll be asked to calculate something like, say, if you remember population projections, there is this uh, cohort based projection, right? Like age wise, you look at the fertility rate. I those can get complicated only because of the number of calculations involved. So it's just about sticking to the calculation properly and keeping the arithmetic clean. The method itself is not complicated, and trust me, we had to do those problems in our examinations. So I'm not sure about the final examination pattern. I will get back to you on this, but hopefully the calculations will be simple arithmetic, nothing too complicated. All right, then if we, I'm really sorry. I also have a sore throat. So if there's nothing else, then we can be done for the day. Hope you all have a good evening.